Okay, welcome to the class, and what we are going to see today is basically the rate matching, idea of rate matching, why this sub-block is there and how it is actually implemented in the standard. Before we get into it, a quick recap of what we have seen till now. We have seen transport block segmentation, okay, which is closely coupled with the LDPC encoding. Okay, that's what we learned in the last two classes, and our running example has been this. A user is allocated 70 PRBs over a slot of 14 symbols, and the user is allocated MCS 16, okay, which has a code rate of 0.642. This information is given in the table once MCS 16 is specified, right? And as soon as this is decided, MAC layer sends a transport block of size this much. Okay, this has to be calculated. Okay, this is not some magic number. We'll calculate it later. And so this is the processing which this transport block undergoes. As soon as it is received at the physical layer, transport block CRC is added, which is of 24 bits. Okay, and then what happens after this is basically it is segmented into four different code blocks. C is equal to 4. That's what we understood in the last class. And if you look at if you dissect this, what is this basically? Okay, so segmentation block, it led to 4 code block, okay, and each code block which is of equal size, which is 7744, okay, plus this is with the filler bit of 672, okay, right. So this transport block gets segmented into 4 code block, and each code block contains 7048 of actual payload, 24 bit of code block CRC, and 672 is the filler bit. Okay, and this is repeated for all the code blocks, okay, except for one difference, that the last code block contains additional 4 transport block CRC, right? Okay, so we saw all this and we understood why filler bit are required. Okay, we discussed that in detail, and now, so if you see this. So this is basically how much is the input size for the LDPC encoder. Okay, LDPC encoder, this will be the input size, 7744. So each code block of size 7744 will be input to the LDPC encoder. Okay, because this is the size of each of this segmented code block. Okay, and we saw this also, that LDPC encoder output, okay, for each segmented code block, how much this is? 66 into ZC. Okay, ZC is the lifting size. Okay, right. And what is this? In this case, it turns out to be, for the example which we took, okay, it turns out to be 352. Right. Okay, and what is this? This is the output. Okay, for each segmented code block, this is the length of the output. Okay, and what it gives us is basically the rate. Okay. Input is 7744, output is 23232, which is 66 ZC. Okay, and what is this? This is exactly 1/3, right? Okay, this is what we saw till the last class. But what does user ask for? User has asked for a code rate of 0.642. Correct? And you see this, that this LDPC encoder is not directly generating this rate. Okay. And we'll understand why this is not being generated in this way, okay, in basically why this output is not directly generated, this rate, okay. So actual code rate is this, okay. Now user has asked for this, okay, and then it needs to be, one needs to generate this code rate from what this LDPC encoder has given, okay. Right, and keep this in mind. What is this? This is rate 1/3, and this is rate 0.6. Okay, so this rate is higher than this. Correct. Okay, this is 0.33, and this is 0.64. Okay, so this rate is higher than this. Now, one question which obviously comes to our mind is why LDPC encoder is not directly generating this rate, right? We saw that in the MCS table. Okay, there are 27 to 28 different code rates which are specified. Now, you will have to, if you directly generate this, if the LDPC encoder directly generates this, then you will have to design 27 or 28 different LDPC encoders. Correct? Okay. Again, it is designing and implementing these so many encoders is a non-trivial task, and it's going to take memory processing power. Okay. Now this task is split between two different modules. Okay. So what LDPC encoder does is it always generates this mother code of rate 1 by 3, and there is another module, okay, which will come later, which generates this rate, higher rate or lower rate. Okay, that's what is rate matching. Okay, that module is basically matches this rate, what is being generated here, this is rate 1 by 3, to the rate what is being asked by the user. Correct? That's why the name rate matching module. Okay. So, and we'll take, so this is one example we are considering, wherein the rate being asked by the user is higher than what the LDPC encoder is generating. It could happen other way around also, okay, that the rate being asked by the user is lower than 1 by 3. Correct? Okay, so we'll take these two cases and see how this rate matcher is designed to match these rates. Okay. So 5G chain which we have seen till now is basically again the summary. Okay. What is happening? Transfer block, append this transfer block CRC, segment it, okay, then append this code block CRC, then LDPC encode. Okay. If LDPC encoding is, as I said, is generating the rate which the user has asked, you don't need that module of rate matching. You can straight away modulate it. Correct? Okay. And then at the receiver side, opposite of this process will happen, wherein like there will be demodulation, there will be LDPC decoding, will be this validation of code block CRC. Then because there is segmentation, you concatenate all these blocks, then validate the transfer block CRC and pass it on to the MAC layer. Okay. But we see this, there is a gap here. Okay. This is always 1 by 3, and there is another module which is basically rate matching, okay, which is required for this to match this rate to the desired rate. Okay, right? And we are going to understand how this works. Okay, I just explained it to you what is the need of it, because we have, with this architecture there is only one LDPC encoder. Similarly, we'll see that there will be only one LDPC decoder also, right? Otherwise, you will have to design LDPC decoders for all the different rates. You could do that. Theoretically, you could do that, and people do it if there is only one rate defined in the system. There are so many rates, okay, right? And writing LDPC decoders for so many rates again is a non-trivial task. Right? If you ask the engineers who are doing it, they'll tell you even like executing one takes its own sweet time. Okay. Right, so that's the idea. You conveniently split these tasks, okay, of like matching the rate to the one generated by the LDPC encoder, okay, which is always 1 by 3. Fine, okay, so we'll see this, how this works, okay. That's the idea, okay. This class and the next class we are going to understand this part. So this is the reference, and this is how it is defined in the standard, the rate matching module. Okay, I should tell you this also, please do not look the standard for the receiver part. Okay, standard doesn't define the receiver. It is only the transmitter which is defined, and you need to design your own receiver. That's a common misconception people have, that they start looking out for the receiver part also. Okay, and that you have to do as a communication engineer on your own. Because if the modulation is defined, you should have studied communication theory to understand how to demodulate it, the QPSK demodulation. And it is not, this is the primary reason, okay, and the non-technical reason is there is a lot of IPR here, wherein like people design their own LDPC, good LDPC decoders. Why should they disclose it to you, to any other vendor, right? Okay, so I'll write a better LDPC decoder, and then my receiver will work better. My mobile will give a better performance. Okay, right? Similarly, all of these modules, I implement them in a cost-effective way. My mobile is going to be cheaper. Fine, okay. So with this, let's start understanding this rate matching module. Okay, so this is our running example. We need to match rate 1 by 3 to 0.642. That's the objective of this class. before we see how that happens, okay, because user is allocated the 70 PRBs, let's recapture our notion of a PRB. How many resources one PRB has? 12 subcarriers over one symbol. And how many such symbols are allocated to this user? 14 symbols. Okay, right? So this OFDM subcarrier is called a resource element in 5G language. Okay, so how many such subcarriers will be there for this user? 12 into 14, 168 subcarriers. Correct? Okay. Now this is something I need to tell you. Okay, it will come later. Out of these 168 subcarriers, not all of them are used for transmitting data. Okay, there are certain number of subcarriers which are reserved for sending pilots. And what are these pilot signals? Pilot signals are basically, let's say you'll send one pilot here, you'll send one pilot here, you'll send one pilot here, one pilot here. Okay, and one pilot in between. Okay, one configuration. Okay, but what are these pilot signals? See, users need to estimate the channel before they can detect the data. Okay, right? Now pilots are these known signals known to the receiver, okay, so that it can estimate the channel from these pilot signals. Okay, how is it different from data? Because data is not known to the receiver. The pilot signals which are known to the receiver, and using those pilot signals, receiver can first estimate the channel. Okay, then only it goes ahead and detects the data. How is it actually done? I'll teach you later. Okay, how pilots are used for estimating the channel, that comes later. Okay, so the point here we are trying to make is that not all the subcarriers are used for transmitting data. There are certain subcarriers which are reserved for sending pilots, and in this case there are 6 of them. Okay, right? So subcarriers for transmitting data, 162. Now using this, okay, how many bits you can transmit, okay, for these 70 PRBs. This is basically number of subcarriers which you can use for transmitting data in one PRB. In 70 PRB, how many you can send? That's what we are going to calculate. Okay, simple 70. Okay, and this number is basically denoted by G, again coming from the standard. Okay, the total number of bits which can be transmitted, okay, for this allocation which is done to a user, G. What is this? How many in one PRB, how many resource elements or subcarriers, okay, name for this 162, and how many bits you can transmit on each such subcarrier or resource element, because it is 16 QAM modulation. Okay, using 16 QAM you can transmit 4 bits on one resource element. We understand this, right? If it is QPSK, you can, using one symbol you can transmit 2 bits. If it is 16 QAM, you can transmit 4 bits. And on each subcarrier you can transmit a symbol, one symbol. Correct? Okay. So one symbol can carry 4 bits because it is 16 QAM. And how many such subcarriers are there? 162 in one PRB. And how many such PRBs are there? 70. This is the total number of bits which can be transmitted using the allocation which is made to this user. And what is this? 70 PRBs using this MCS. Right? This is what can be transmitted. So total number of segmented code blocks, how many? 4. C is equal to 4. Okay. So these are the total number of bits you can send over this assignment. Okay. And number of bits allowed to be sent for each segmented code block, that is denoted by E. How many it will be? These are the total number of bits, right? So per code block, how many you can transmit? G by C, right? Okay, because you need to transmit all the 4 code blocks. So what is this? 11340, right? Okay, understood the sequence? Okay. Now for our example which we are taking, how much was the input length? Okay, how much is the size of this segmented code block? 7744. Okay, and how much was the output length? 66 into ZC, which is this, right? Okay, so this, and that's what we saw. Mother code rate is 1 by 3. 7744 by this number gives you 1 by 3. Correct? Now see this. How many bits you are generating using this code rate 23232. This is the LDPC encoder output, correct? And how many bits you are allowed to send per code block? 11340. We understand this, okay? And what is actually happening here? You are generating more number of bits than what you can actually send, okay? And the reason should be clear to us. What is this? The code rate, the mother code rate which you are using is 1/3, okay? So what is happening? For every bit you are generating 2 parity bits. What is the code rate the user has asked? 0.6, okay? Right, that's actually close to 2/3, right? Okay, so what does that tell you? That code rate, instead of for 2 message bit, you should generate only 1 parity bit approximately, right? Okay, but you are generating 2 parity bit for 1 message bit, which essentially means that you are generating more parity bits than what you could actually, what the user has asked for, or what you could actually send. So what do you need to do? You need to drop these parity bits at the transmitter, and that's what is rate matching, okay? And by dropping these parity bits, what are we doing? We are converting a lower code rate to higher code rate, okay? Fine, because here you are generating extra parity bits. So the common way of generating a higher code rate from a lower code rate is you drop these parity bits, and the technical name for this process is called punching, okay? So you puncture the bits, right? And now we see that, okay, right? So actual rate, by considering number of bits allowed for each segmented code block, which is 11340, these are the this is the number of bits which is allowed to send. We just calculated here, okay? Now look at this. So instead of k, I am writing k dash here, okay? Why? Because k contains filler bits also, right? Filler bits are not actual data, right? And I will show you those filler bits get dropped at the transmitter, okay, because they are dummy bits, and those dummy bits were inserted for the LDPC encoder to work, right? Okay, so what's happening here? So this is the number of bit which is allowed to send. K, what is the relationship between k dash and k? What is this? Okay, k is 7744, right? K dash is basically, how are you getting k? You are taking k dash and adding 672 filler bits to it, okay? So what is k dash? This divided by e, okay? So this should be divided by e. I missed this e here, okay? So which is 7072 by 11340. What is this code rate? 0.623. Okay, you will see that it is not exactly 0.64. It's okay. Okay, user has asked for 0.64. It's not guaranteed that he'll get 0.64. You should not give the user more than 0.64. That we understand. Correct? Okay, right? So what are we ensuring here? We are ensuring a code rate close to what user has asked. And if you carefully see, okay, this k dash contains 24 CRC bits also. So if you remove them, if you subtract them further, it will slightly go lower than 0.623 also. Okay, so I just, for the sake of like convenience, I did not subtract it. Okay, but the actual code rate is that, right? Because that's the message bit divided by the number of encoded bits you are sending. Okay, so it's 0.623. So what is this rate matcher supposed to do? In this case, it is supposed to drop the bits right at the transmitter, okay, right? And how this is handled at the receiver we'll see later, okay. So what is its equivalent module at the receiver? That's what I'm going to teach you also, okay, but hang on. So this is what we are trying to understand here, okay. So we are calculating the rate by removing 672 filler bits. That's what we have done, okay. So you're getting 0.623, okay. Now, so this is the idea of rate matcher, okay, principle behind designing a rate matcher. To summarize why this rate matching is used, the LDPC encoder is generating at the mother code rate of 1/3, which is not the same as the one asked by the user. user can ask for a code rate which is higher than 1 by 3 or lower than 1 by 3. The example which we are taking, user has asked for a code rate higher than 1 by 3. Okay? And what is happening here in these slides, what we have seen is that the transmitter needs to drop the bits to generate a code rate which is higher than the mother code rate. Okay? That is the idea. And why it is being done like this? Because of to simplify the implementation. That's all. Otherwise, in principle, there can be different LDPC encoder for different rates. Nobody is stopping us from doing that. Okay? But then the mobile will become costly, it will run out of battery very soon. Okay? Because processing power involves battery. It will become costly also. You don't want to do that. Okay? So with this in mind, let's see how it is done in the standard. Fine? Okay, let's go ahead and see that. So this rate matching module is, one task is basically to match the code rate. Okay? And you will see that it has another task also, which is the implementation of hybrid HARQ. Okay? Right? If you remember, when we were talking about hybrid HARQ, we spoke about different RVs, redundancy versions. What were those redundancy versions? Different parity bits. Correct? If it is chase combining, then you retransmit the old bits. If it is incremental redundancy, what do? You transmit fresh set of parity bits. You will see that also it allows us to do that. Okay? Right? So it's a nicely done framework. Okay. So what happens here is, what module it succeeds? This is an LDPC encoder. Correct? Okay. So what am I saying here? This LDPC encoder is directly written in a circular buffer. What is the circular buffer? This. Okay. You forget what each one of this is, the inner arrow. Okay. And what is this RV0, RV1? All this I am going to tell you, right. So this is a pictorial representation of a rate matching block. Okay. And what is this? This is a memory, that is all. At the end of the day, okay, what are we doing? LDPC encoder has generated certain bits. We are supposed to be reading those bits and dropping certain number of parity bits. Okay. That is what it is supposed to be doing. Now, so this is a circular buffer. Circular buffer is basically, if you reach the end of the buffer, you start reading from the beginning, from the starting location. That is what is circular buffer. Okay. So you see this, they are not disconnected, end is connected to the beginning. Okay. Correct. So now this LDPC encoder is directly written in a circular buffer. Bits are read from the buffer starting from an offset position and increasing the bit index. Okay. So what are we saying here? What is this bullet saying? That you write this into all those bits, rate 1 by 3, okay, k bits which you have generated, okay, you write all of them in this circular buffer. Okay, fine. Okay, sorry, not k, it will be n bits. K is the input, LDPC encoder will generate n bits. N is what? 66 ZC. Correct? Okay, so the length of this buffer will be n. Okay, right. So what happens here is, if it is, let us say, the first fresh transmission, and we are transmitting RV0, redundancy version 0. Okay, right. So what will happen here is, you start reading from the beginning of the buffer. Okay, and how many bits you are going to read? What is this? This is E. What is E? E is equal to G by C. Remember this. Correct? Okay. So you are supposed to be reading only E bits. For each segmented code block, you are allowed to transmit only E bits. Okay. Right. So what is happening? The length of this circular buffer is n, and you will read only E bits, because that is all you are allowed to transmit. Okay. So that is what we are saying. So you start reading this. right? You are done. Fine, okay. Now these bits are transmitted, they undergo rest of the transmit processing also, but at the receiver, if it is this packet or this code block is detected fine, right, then you will not retransmit it, transmitter will not retransmit it, correct? Okay, so it's done, right? Okay, now if the receiver is not able to decode it and it sends a NAC, what will happen? Okay, and the transmitter decides to send another redundancy version, okay, right? So what will come back, transmitter will come back to the same circular buffer. So these bits will be stored in the transmitter memory, okay. What will happen here is, so redundancy version 1, RV1, okay. So it starts from here. What is happening here? You are sending some old bits and some fresh parity bits, right? Then this is hybrid ARQ has kicked in, okay. If the receiver sends a NAC, then RV2 will be transmitted. This begins from here, RV2 position begins from here. Read this, correct, okay, and this is E, it will send that, okay. Then if RV3, then it will happen like this. See this, now the circular buffer is kicking in, right, okay, because you will have to read few bits, the new bits and some of the old bits, correct, okay, right. So what is happening here? When I send the first RV, I am sending only E bits, and the rate is matched, correct, okay. And then when the NAC is sent, then we are reducing the rate. If I send the same RV, then I am not reducing the rate, I am increasing the SNR, because that is the chase combining. If it is RV1, I am using the IR flavor of the hybrid ARQ. So nice, everything gets done in the same block, okay, right. So if the bit index reaches the maximum number, the bit index is reset to the first bit in the buffer. That is what is happening over here. That is the circular buffer part, okay. Redundancy version specifies a starting point in the circular buffer. So what is hybrid ARQ implementation reducing to? It is only reducing to a starting point in the rate matching buffer, that is all, correct. So if it is simple case to understand, if it is you do chase, what will you do at the receiver? You will simply add these bits. If it is this, then you will have to do something more sophisticated. I will teach you that, okay, because you are transmitting some old bits and some new bits. So what do? Some old bits you add, certain new bits you leave them as such, right. So that is what it is. Actually we have understood how it is done, okay. So different RVs are specified by different starting points. We understand that because different starting points implement different versions of or different flavors of hybrid ARQs, correct, okay. RV0, start from RV0, chase, all other RVs will implement chase, incremental redundancy. So what is this? Usually RV0 is selected for initial transmission to send as many systematic bits as possible, and this is again the idea of LDPC. This is a constraint of LDPC because LDPC requires maximum number of message bits to successfully decode the message, okay. We have understood that in great detail, okay, right. And scheduler can choose different RV to support chase and incremental redundancy. This is something you should know. There is an additional piece of information that systematic bits are also punctured, okay, which means that RV0 will not start from the beginning. I have shown it here, okay. It will be standard drop certain number of message bits also, okay. Again, people have realized that this kind of, if you puncture these systematic bits, it leads to better performance at high code rates, okay. LDPC decoder will give you a better performance. They are all coding related ideas, but you should know why this is being done. If you want to read about it, there is something more in this paper, okay, right. So how many bit it punches? Punches 2 ZC bits from the encoded output of the message bits. What I am saying here, RV0 will not begin from the beginning, they will begin with the offset, fine, okay, right. So and then this rate matching modules calculate this redundancy version starting point also, okay, because who tells you this? RV0, RV1, That's also a part of the rate matching module. I'll give you that formula at the end of this class. Okay. So, and what is it doing? It basically calculates number of bits to be read for each of the rate 1 by 3 encoded block. That E is equal to G by C calculation is also a part of this rate matching module. Okay. Fine, we get that. Okay. So, what is this? That's how it is implemented. This is the standard implementation. I will give you the instructions also in the next class how it is implemented. Okay. So, this is our example. We come back to our example which we are taking. How many code blocks? Segmented code blocks. C is equal to 4. What is this? 11340, which is E. This is the number of bits which is allowed to be transmitted for each code block. So, what happens? What is the length of the circular buffer? That is what I said, N. Correct? N will be the length of the circular buffer. How many bits you are allowed to read? 11340. So, this is the RV0. You read these many bits. That's all. You leave all these bits as such. That's what was the circular buffer, right? Instead of writing it, showing in a circular manner, I have like unfolded it and I am showing you like this, right? So, if it reaches here, it will go back, but in this case, it is not. Right? It will stop here. So, this is the first rate match block. Same. You look at the second rate match block, second encoded output. You read how many bits? 11340. Right? So, this is the second rate match block. Similarly, third rate match block, how many? Then there will be fourth one. Correct? Okay. So, there will be 4 different circular buffers for 4 different code blocks. Correct? Is this clear? Right? Okay. So, that is what is happening here. So, now this is how RV positions are calculated. Okay. This is the final slide of this class. So, you see this NCB, what is NCB? Is the length of the circular buffer. It is set to N in our case. Okay. These are some numbers. Here for LDPC base graph, we are setting it to 0 here. Standard, there is another flavor where it will not be. As I said, some certain bits are dropped in the beginning also. Okay. So, you see this here, RVID is starting from 0. Okay. And this is the second LDPC base graph. Okay. 2 LDPC encoders are there. Correct. Okay. And for RV1, for RV index K0 is equal to 0, so it will start from the beginning. Okay, whatever I mentioned about dropping those bits, that also happens. Okay, but here for this is RV index is set to 0. Okay, rest all indices you will see. The first one begins from 5984, second one K2 begins from 11616, and this begins from 19712. This is the formula. And that's how it is calculated. Okay, right, and this helps us in implementing the hybrid HARQ. So, rest, we will take another example in the next class and we will see how basically if the receiver has asked for a code rate lower than rate 1 by 3, how does rate matching help in that case. Thank you.